All right, class, this is our fifth and final video on section 3.7, polynomial inequalities. We're covering page 5 of your lecture note handout and example 4, the fourth and final example on this topic. So in this video, we're solving the polynomial inequality 4x minus 9 to the fourth power times x minus 1 to the third power times x plus 1 and less than or equal to 0. So we're going to find all the real numbers we can put in for x on the left hand side so that the value of the left hand side is less than or equal to 0. So first step, find all the values of x that make the left hand side equal to 0. So we set the left hand side equal to 0, apply the zero product property, and we get x equals 9/4, x equals 1, and x equals minus 1 are the three numbers we can put in for x up here, and the left hand side will equal 0. We then use those three numbers, we plot those three numbers on the real number line and to divide the real number line into 4 intervals. And you will notice that when I plotted these three numbers, I have closed circles, not open circles. And that's because these three numbers are in our solution set. These three numbers make the left the left-hand side up here equal to 0. And in our solution set, we're including the values of x that make the left-hand side equal to 0, not just less than 0. So we divided up the real number line into 4 intervals using the real roots of the factored polynomial. And now we apply the test point method to each of these 4 intervals to see whether the polynomial is positive or negative on each of those 4 intervals. So the first interval goes from minus infinity to minus 1. The second interval goes from minus 1 to 1. The third interval goes from 1 to 9/4. And the fourth interval goes to 9/4 to infinity. Again, these are open intervals with parentheses. We already know that minus 1 is in the solution set, plus 1 is in the solution set, and 9/4 is in the solution set. We want to see if the other numbers, which of the other numbers are in the solution set. So in the first interval, I use minus 2 as my test point. When I plug in minus 2 into the factored polynomial, I got a positive value for the polynomial, and so that's the result. And so that tells me any real number less than -1 put into the polynomial, put in for x in the polynomial, will result in a positive value for the polynomial, a positive number. In the second interval, I use 0 as my test point. And when I put in 0 in for x in the polynomial, I got a negative value for the polynomial. So any real number greater than -1 and less than 1 put in for x in the polynomial will result in a negative value for the polynomial. In the third interval, I use 2 as my test point. When I put in 2 in for x up here, I got a positive value for the polynomial, right? It's equal to 3. When x is equal to 2, the polynomial is equal to 3, which is a positive number. So that tells me any real number greater than 1 and less than 9/4 put in for x up here will result in a positive value for the polynomial. And then lastly, in the fourth interval, I use 3 as my test point. And I put in 3 in for x up here. I got a positive value for the polynomial. And so that tells me any real number greater than 9/4 put in for x up here results in a positive value for the polynomial. So again, we don't want to lose sight of the inequality symbol. We're looking for all the values of x that make the left-hand side less than or equal to 0. And so less than is negative. And so you can see that of these 4 intervals, only one interval makes the left-hand side of our inequality negative. So the interval from -1 to 1 is in our solution set. These other 3 intervals are not in our solution set. So I've graphed the solution down below. And so the numbers, real numbers from -1 to 1 are shaded in. along with -1 and +1, because -1 and +1 make the left-hand side of our inequality equal to 0. So they're included in our solution set. And then the other three intervals are not open intervals, are not included in our solution set, but we have one value of x all by itself out here, x equals 9/4, that is in our solution set, because x equals 9/4 makes the left-hand side of our inequality equal to 0. And we want all the values of x that make the left-hand side of the inequality equal to 0 or less than 0. So 9/4 is in our solution set. So we see the values of the polynomial are less than or equal to 0 if, right, less, this is important here, less than or equal to 0 if x is greater than or equal to -1 and less than or equal to 1, or if x is equal to 9/4. So in interval notation, our solution is all the real numbers from -1 to 1 in brackets, because we're including -1 and 1, and then we have to include this single number 9/4 to our solution set. And so that's not an interval of numbers, that's just a single number. So we join that one number to this interval of numbers from -1 to 1 using set brackets. Right? These are set brackets with a single number 9/4 in it. So this is a set with just one number in it, 9/4. And so in interval notation, our solution set is -1 to 1 in brackets, union 9/4, the number 9/4, and set brackets.